All right, let's go over the vertical mill today. Our shop has two Bridgeport knee mills. We will cover basically what the parts are, how to move them, what you need to know to load and unload a bit, how to turn the machine on and off. So we'll go through all that before we dive into actually making our first parts. So let's start over here on this side. Just to name the parts of the mill. The base, obviously, is what everything is sitting on. Then you've got the knee here. That's the name of the knee mill. On the knee sits the saddle. The saddle moves back and forth in the Y direction. Then on top of the saddle sits the table. The table is able to move back and forth in the X direction. And then the entire assembly itself sitting on the knee is able to move up and down in the Z direction. In addition to the knee moving up and down, the quill, which we'll talk about in a second, is able to come down as well. So we have two ways of adjusting our vertical height on that. When you are machining in any particular direction, that direction will be in movement, but the other two directions will not be. And it's important to lock those off. So if you are not changing your Z direction, you'll want to lock those off. Those locks are down here. Locks the knee. If you are machining in the Y direction, you're going to want to lock off the X, which is the cross table here. So you lock those off in this direction, then you can still move your Y. Conversely, if you're going to be machining in the X direction, you would unlock these, and then go ahead and lock up the Y direction here, like that. So if I lock that down fairly snug, it's actually quite difficult to move those knobs. So those are loose. Those are loose, and these are loose. Then you're free to move the machine around in X, Y, and Z directions, and so forth. Let's talk briefly about how the machine is actually put together, how we hold these tolerances, and how everything is kept tight without, or with a minimum of slack and play. As you can see here, there are these dovetail ways. These are precision machine ground, and they match up precisely with the parts, in this case on the saddle over here. There is a second piece that cams in behind there. There's a threaded screw behind the table here that you can adjust to tighten that up and take any play and so forth out of there. Over the life of the machine, these ways will wear down a little bit, and so you do need to take adjustments on that over time. If you're the first person of the day to the machine, it's a good idea to lubricate or ensure that the machine has already been lubricated before you start working on it. Ours have what's called a one-shot oiler, so if you step around behind the table, pull this little lever up and just let go. It's spring-loaded and it pulls a little bit of oil up out of that reservoir and pushes up through a series of tubes and lubricates each of those ways. If you don't lubricate on a regular basis, you get a lot more wear of those. Your machine will wear out more quickly. If you do the lubrication step on there, then everything's sort of floating on a nice thin layer of oil. So these guys will run nice and smooth. Run there. Okay, each of the axes also has a graduated scale to it, which allows you to move them in very precise thousandth of an inch increments. Our Y is adjusted here on the front, and you can see if I kind of zoom in on this here, that scale can be adjusted there. So each line is about a thousandth of an inch. We can loosen this knob here, and this allows us to swing that scale without adjusting the axis. And this would allow us to move the part into position and then zero out our axis and then come back and lock that off. Now we can move a specific amount from the point of known, zeroing off something with our edge finder, so forth. We don't use these as much because we have our digital readouts now. Make it a little bit easier to do that, but they're always there. In our Z direction, we don't have a digital readout, so this one does become more important. You'll notice the handle on this guy is actually reversed. This swings around like that. And they make this come off easily because it's really easy as you're walking around on this machine here to clip your knee or something on that. Maybe that's why they call it a knee mill. I don't think so. But anyways, we're not using that axis. You can tuck that up out of the way like that, just like so. As we mentioned, the y-axis is here, the z-axis is here. Both of them have that scale on there to allow you to adjust them in precise known amounts. The table's a little bit different. We have two ways of controlling the table. So both ends have the same micrometer set scales on there, but you can control them from this side as well as from this side. Kind of depends a little bit if you're left or right-handed or what side of the part that you might be machining on. In general, I like to stand to the right side of the machine. Control your Y here, your X here. The way our machines are set up with the digital readout on this side, it's a little bit easier to see it and so forth. And then you can turn around this side, adjust your Z axis if you need to, and you're a little less likely to bump into things as you're running the machine. So we talked about the movement of the X and Y axes and the ability to use these micrometer indications on the knobs themselves. And I mentioned the use of digital readouts, DROs, as making life a lot easier than having to use these guys and constantly zero these things out and so forth. So our digital readouts are located up to the right side of the machine here. And we have our X and our Y. Y corresponds to the movement of the table and saddle, usually towards and away from you. X is the movement of the table on top of the saddle, across from you, back and forth across. These can be zeroed out simply by resetting the axes. So you'll see now, as I move this guy, say roughly 100 thousandths forward, we got 792 thousandths on our digital readout. So that agrees really well, doesn't it? This is an important time to bring this up. There is quite a bit of play or slack in the movement of the tables. This gets worse as the machine gets older over time, but it's inherent in all machines and just the way the screw mechanism works for actually moving them forward. So on this machine, I can see, let's go ahead and zero this. Set this right at 0 there. Everything's tight. And then I'm going to go ahead and zero our digital readout in the Y. Now, I was traveling in one continuous direction moving this way. So there's sort of tension in these gears or in the screws here. So now if I rotate this forward to 100,000, we get on our digital readout 994. Which is 99 because we're not counting the last 4 10,000ths or whatever on this scale here. I can tap this gently and to get that right at 0.1, 100 thousandths of an inch. The reason I bring that up, now we're at 100, that agrees with both scales on there, more or less. Now if I decide that I'm going to back that up, if I were only using the scales on the knobs here and I just back this up, there's this, I can feel the slack in here to about 85 or so. And you'll notice as I do this simultaneously between two cameras, as I move this back and forth, our digital readout is not moving at all. It's not until I catch this and actually start engaging those threads and pulling the table forward that I can actually move this over. So now I'm going to bring this back to 0 on here, and we'll look at our digital readout. 194 10,000ths of an inch there. So, or 19 thousandths. That's how much play we have in the table. So one thing that's really nice about these digital readouts is they're taking the absolute position of the table. So I don't really have to account as much for that slack that's in there. As long as I remember to lock those tables off, those little lock handles on there. In fact, you'll see sometimes as I lock those down, it'll change the digital readout just a little bit. If that's locked off and that digital readout is reading that number, then you can be sure that your table is in that position, regardless of this little bit of play that you see in the handles down here. Not every machine has a digital readout, and I just want you to be aware of this little bit of play that you have in machining. And if you were ever in a machine shop with a more analog type machine, that you can compensate for that, because that can really make some big mistakes in your parts and stuff if you don't. So working our way up the machine, we mentioned the base, the knee, the saddle, the table. On the table itself, there's sort of two ways to use it. We typically use it with a vise. It's a lot easier to move parts in and out. However, if you have a really large part that wouldn't fit in the vise, it is possible to clamp it directly to the table, a series of keyways on here. This work stop part that's on here now is tightened in there with these sort of channels that have a groove underneath there, and those parts are keyed like so, and those will fit on there. Our vise as well has the same sort of little key nuts on the bottom there, and that allows us to clamp the vise to the table. Using a vise is nice. We'll talk a little bit later. We can ensure that the back of this jaw is completely squared up to the table. Each time we move in and out, a part in and out of there, we'll be sure of that. If we're clamping directly to the table, then each time we do that, unless we put up some careful stops in there, we'd have to realign the part and make sure that everything is straight on the table. So working our way up, as I mentioned, the vise here, we have your immovable or permanent jaw on this side. This is the mobile jaw. Self-explanatory, those move back and forth. When we get to machining our gyro frame, I'll talk a little bit about some of the parts that can be swapped in and out of these vices. Working our way up from that, we'll move into the actual head of the machine here. Many of the levers on here we won't use for any of the operations that we'll be doing in this class. They primarily involve having the quill, this part here, being power fed down. So if you want to drill a series of holes, or sometimes even doing some tapping, you can use the power feed feature on this, which is similar to what we'll talk about a little bit on the lathe. It just allows some automated movement of the head. So I mentioned the quill, that's attached to this lever here. It can be swung around similar to the lever for the knee. Put this in a convenient position for what you're doing. Move your quill down to this position. Maybe it's a good idea to get this out of the way. So that can be swung around wherever it's convenient. Within the quill, the part that's actually spinning is the spindle itself, and we'll talk about loading collets and bits in and out of the spindle in a little bit. On the quill itself, I mentioned the Z as one way of, the knee is one way of changing our Z axis. The quill is the other way. Typically what you would do is bring your bit down to your part, touch off, lock your quill in place with this little lever here, and then make adjustments with your graduated scale on your knee over here. So you need to make a cut of 40,000 steps. You would touch off up here, lock this thing off. It doesn't have the precision of scale in here. Then bring your knee up that 40 thousandths that you need to meet the bit. So the machine itself has two speed ranges depending on the size of the bit, the type of bit, and the type of material that we're going to be cutting. We have different speed ranges that we need to select for. A high range and a low range on this guy is shifted back and forth with a transmission, an actual geared transmission up here. And then there is this lever on the front here with the turtle and the bunny rabbit. Our turtle will be our low range, the bunny rabbit will be the high range. It's important to never adjust this speed unless the machine is actually running. Seems counterintuitive to what a lot of machines, set the speed, then turn it on. Completely it is the opposite with this guy. This is a variable speed drive. It's got a series of, I think, rubber-shaped cones and belts in there. And it's important that you not adjust this unless it's actually running. So we'll do that in just a second. The other thing that's important, try to work between two cameras here. You'll know, so that was our gearbox, high and low range. We also have the switch box, which is actually turning the electrical motor on and off. It is up for the high range, down for the low range. So it's important when you're running the mill to make sure that your high range on your electrical switch selector box is in agreement with the high range in your gear shift box. If they are in disagreement, one's high and one's low, either way, it'll actually turn your bit, your spindle, in the opposite direction. So normally we're cutting in a clockwise, looking from above. We'll actually spin our bit in a counterclockwise. Maybe there's some times when that's useful, but in general, we always want our bit to be turning in the clockwise direction. I'm just going to confirm that I'm in high speed over on this side, high range over on this side, and before I go any further, I'm going to put on some safety glasses, also magnifying glasses. So I'm going to go ahead and turn it on. That's it, our machine is running. I'm going to move this camera around here so you can see the speed adjust. Hopefully you can see that okay there. So right now we're running about 1450 RPM or so. As I run this little wheel, you can hear the motor run up, 25, 24, 2600 RPM. Conversely, we can run that down. Like so. Okay, so I'm gonna switch the machine off. There's a little brake here. We'll talk about that again in a second for switching bits out. So stop that spindle from rotating. Now I'm gonna go ahead and press this lever in, swing this around, and let it pop back out. And now we're in the low range. And if I step back over to this side again, I'm going to switch our box down this time. And now we're going to read off the scale with the little turtle over here. So we can run, all the way down to about 190 RPM or so. And we're running all the way up to 200, 240. The high end of this will roughly cross with the low end of this scale here, so you have a continuous range of speeds from probably roughly about 50 all the way up to probably about 3,000 RPM or so. All right, and we'll hit the brakes. Okay, let's go over changing bits now. We've gone over how to turn the machine on and off. Now we need to know how to load our cutting bits into the machine. This is an example of a 2-flute, 2-ended end mill. Probably can't see this in the camera, but it's reading on there a 3/8 inch end mill. So we need a way to securely hold that in the machine in order to do our cutting. In order to do that, we use a series of collets. I've got a series up here. Each collet is designed to fit up into the machine, has a tapered fit that'll grab the bit on there. But each collet is sized specifically for a particular size of bit. Unlike a chuck for a drill bit, which has a wide range of adjustability, these are intended for a very specific, very precisely machined size. So this is a 3/8 inch end mill. I've got a 1/2 inch collet there. We need to find our 3/8 collet, 7/16, 9/16. All right, well, luckily we can edit this down. Where is our? Okay, so I found a 3/8 inch collet. You can see here how the tool will actually slide into this collet. It's a fairly snug fit. Press that in there, and then we want to make sure we get past that keyed spot on there and make sure that the collet, most of the gripping force of the collet is up here in the last inch or so. So we want to make sure that we go up to just before the cutting threads, maybe 1/8 of an inch or so out from there like that. Now you'll notice on this collet here, there's a keyway in it as well, running the length of it there. There is a little pin inside the spindle here, and that keyway will need to line up with it. In addition, the back side of this is threaded, and there's a long drawbar, it's called, that runs down through the quill and will grab our collet, pull the collet up into the machine, and as it pulls up, the matching tapers and the spindle and on the collet here will cinch down on your bit there. So I'm going to slide this up underneath there, rotate it around until we line up. There we go. And it's a little bit of lift, it's a little bit of play in here. Again, let's see if you can get you down here a little bit. Okay, so when we load the collet up in there, you can feel a little bit of lift on there. That's actually lifting the drawbar up on top. If for any reason your drawbar isn't showing all the way up there, or maybe isn't showing at all, you need to raise your quill all the way to the top position there, and you'll see plenty of drawbar sticking out at that point. So continue to hold this. Sometimes people will hold this with a rag or something. A brand new bit can actually be razor sharp. So hold this with a little bit of pressure up. Turn your drawbar up here at the top, and you can do this hand tight, and you can watch us actually drawing the collet up there, like so. And I snugged that, and this was a nice tight fit on there, but sometimes the bits are a little loose, may want to fall out. So you'll want to make sure that you get that at least finger tight, and that your bit isn't going to fall out on its own. Now that needs to be tightened up. We use a wrench up here on the top on this guy. There's a little trick for making sure that you can get that tight. If we just put the wrench on there like so, and I just turn it. You may notice that the entire spindle is turning. That bolt is turning, but it's actually turning the spindle down here as well. You can see that back and forth on there. So in order to keep the spindle from turning while we're tightening it up, there's a little brake lever here on the side. You can push that away or pull it towards you, push that away. Hold that down with a little bit of pressure. That puts a little brake on the spindle, and you can tighten that off. And it just needs to be snug. No cranking down on this thing very hard. It's often that students, anybody will crank on that so hard that it gets very difficult to remove it. Remember, this is a tapered fit, and it doesn't take much force to really wedge a taper tight. I'll demonstrate that actually on the lathe in a little bit, how it doesn't take much force at all to lock a taper off. Now, it's important to never take your hand off of this wrench up here because that bolt is attached to our spindle. If we leave the wrench up here and turn our power on, that wrench is going to spin with the spindle, and I don't want to know what's going to happen when that wrench goes flying off of there. Anyway, so never take your hand off. There's no chance of forgetting leaving that up there, turning the machine on, and having that wrench let loose up there. Keep it down here on the table with you. I'll sometimes put mine on the back of the machine like that, out of the way. All right, so we've tightened our tool down in there. Our gearbox is in the high range. Our knob will turn on to the high range. And it's hard to see probably with the speed on there, but we are spinning in a clockwise direction. As I said, we can slow that down, 500-600 RPM there, something like that. Maybe we can see that on the camera. All right, turn it off. If you're not patient enough to wait for the coil to stop, use this as a brake to slow that down. Okay, so once we're done with a particular bit and it's time to change it out, removing the bit is more or less the reverse process of putting it in. Except that when we've tightened down on that drawbar, it's, as I mentioned, pulled those tapers pretty tight together, and sometimes they don't release, especially if you're overzealous on how tight you tighten that down. It can be wedged up there in there pretty tightly. So to get it out, we're going to take our drawbar wrench, we're going to go ahead and lock off the brake. I'm just tall enough to reach up and do this. So lefty-loosey, and get this just to the point where it releases, and you think you can do it with your fingers, because we don't want to drop this bit out and have it drop onto the vise or your part. Sometimes you can take a rag or something like that to help ensure that, but especially if you're using carbide, which is exceedingly hard, if that drops out, you can chip your carbide, you can leave dings in your part and so forth. Ideally, you've done that just to the point where it's finger tight now, and you should be able to loosen your drawbar just a couple of turns. If you loosen it all the way out till it's coming loose on there, and then you tap on it with a hammer like we're about to do, you can damage the last couple of threads of your drawbar. So it's a good idea to just one or two turns, loosen that up. Now our taper has locked this bit in there. I still can't pull that out. So we'll use something like a dead blow hammer and just gently tap on top here, and that should release, just like that. All right, then we can take our bit out, and then we can continue to unthread that drawbar, hanging onto our collet like so.